who are cutting down a tree or something. At any rate, they're operating a chainsaw, it sounds like. So from time to time, if you hear some mechanical noises, hopefully we can struggle through and they won't make too much noise. So we're seeing this thing on the screen here before, these data types. And remember, on the 32-bit machine, you get some slightly different things when you compile your C program than if you compile it for a 64-bit machine. And the ones that are different are the long int. On a 32-bit machine is simply same thing as an int. But on the 64-bit machine, you do actually get a byte quantity for the long ints. The long double on the Intel, you get this internal extended precision thing. And on the 64-bit machine, you get a 16-bit, 16 byte, I should say, quantity. The only other difference is, of course, an address, the size of an address. So pointer to character, pointer to anything, could be pointer to integer, pointer to long, pointer to float, whatever. It's an address. On the 32-bit machine is 4 bytes, and on the 64-bit machine is a 64-bit address, right? So remember those sizes. So now we want to look at the 64-bit architecture, see how it's different from the 32-bit architecture. The 32-bit architecture, you'll recall, we had a total of 8 registers. And they had all these names like EAX, BA, EBX, ECX, those kind of things. On the 64-bit machine, we have twice as many registers. We have a new set, 8 registers over here. And all of the registers are twice as wide. They're 64 bits wide. You can still play with the 32-bit registers. They're just the right portion of the 64-bit register. So we use names like RAX to refer to the 64-bit register and EAX to refer to the right side, or the 32 bits on the right of the 64-bit register. So this is the AMD 64-bit idea for extending the 32-bit architecture that eventually Intel came around and mimicked this same scheme. Now, the nice thing is that all of your 32-bit instructions still operate on these 32-bit registers, the right sides of the 64-bit registers, and behave completely identical to if they were running on a 32-bit machine, which is what you want. The thing you need to realize is that when you run 32-bit instructions on the 64-bit computer, that when you, for example, load the EX register, you use that instruction, it zeroes out the high bits in the 64-bit register. So anytime I do a 32-bit instruction loading one of these registers, it automatically zeroes out the rest of it over here in the 64-bit register. Other than that, you get the exact same behavior for your 32-bit code running on the 64-bit machine. And you say, well, why do I care if my 32-bit code runs on the 64-bit machine? Well, running on this computer, you'll see a lot of these say 32-bit, right? Those are 32-bit programs running on this 64-bit machine. And so there's a lot of code out there that is still old 32-bit code that runs on these 64-bit machines. And so if you have a company that produces a product and your product is running just fine on the 32-bit machine and then the 64-bit machine out, well, you don't want to have to develop an entire new product and support two sets of code, one for the 32-bit machine and one for the 64-bit machine. So it might be easier or cheaper just to have one version of your code that targets the 32-bit machine, and it'll still run on all those 32-bit machines out there. And it'll also run on the 64-bit machine, and you don't have to maintain two separate pieces of code, which would be a more expensive proposition for your company. So there's a lot of stuff out there that even you get a brand new program, it's still a 32-bit program. So it's important that we can run all those seamlessly on the 64-bit computer. But they're not taking advantage of these wider registers and these extra registers that we have when they're running in the 32-bit code. Okay, now the names of the new registers are simply 8 through R15. They don't have these old legacy names that are left over in the case of the 32-bit machine from the ancient times when the instruction set was less orthogonal and you had to put specific things in specific places. So the names, we have a nice orthogonal machine now. So it doesn't matter whether I put it in 10 or 11 or whatever. So they just name them register 10, register 11, whatever. This is more like a RISC computer. If you look at a RISC computer, they just name the registers R0 through R31 or whatever. They have however many registers they have. So RISC machines are going to tend to have a lot more registers, fewer instructions, and less complicated instructions. So the 64-bit AMD 64 architecture is kind of got a little flavor of a RISC machine in that we have these extra registers now. So it's kind of a little of both. It's got its CISC heritage and a little bit of flavor of RISC. And we'll see that the parameter passing conventions are different on the 64-bit machine. They're more like we would do it on a RISC machine. So the new instructions, just have counterparts. The old 32-bit stuff, we were using L for long word, move a long word. Now we have move quad words. We have new instructions that operate on the 64-bit registers, and they just mimic all of the instructions you already had on the 32-bit computer, but you can do 8 bytes at a time now rather than just 4. All the old 32-bit stuff still works. And like I could say, move long word something to the EAX register, and that would still behave just like it always did. So setting the higher order bits of the destination register to 0 happens whenever I do a 32-bit instruction, like add long word or something. So let's look at our swap code that we were looking at on the 32-bit calling conventions. We had the business where we were reaching back up the stack here to get the parameters that were being passed in. We went 8 back. You had to jump over the return address that's sitting on the stack and the saved base pointer that we saved up here, BP. We put ESP in the BP. So if you go, this is going 8 back, jumping over where we saved that off and where we the return address. So at any rate, the 32-bit convention was to pass the parameters through the stack, right? Like this. And we look at the 64-bit calling convention. We're not going to pass the parameters through the stack unless we have more than 6 of them. We're going to use registers. We have all these registers now, so why not use them to pass the parameters rather than touching memory? Because touching memory is the most you can do. It's several orders of magnitude slower than any instruction you could execute on the computer. So minimizing the number of times you have to touch memory is a good thing. So now we're going to have a convention that says the first parameter on the 64-bit computer, its calling conventions, is going to be in the RDI register. The second parameter is going to be passed through the RSI register. So the caller loads up these registers with the things it wants to pass in, and the callee just assumes they're already there. And so you see that the code for this now is just saying, oh, take what RDI points at, this address you passed me, pick up that memory location and put it in this EDX register. Notice that we're still moving a long word because this is an integer, 4 bytes, right? We're picking up 4 bytes out of memory, putting it in the EDX register. Now, the second parameter is in the RSI register. So we're picking up 4 bytes and putting it in there, and then we just stuff them back into the opposite places like we did before. And since we didn't do all this little stuff about saving off the BP and moving the ESP to the BP, we don't have to pop the base pointer and all that. We just return. So we saved ourselves some instructions, and we saved touching memory many times, but it's kind of a hidden thing going on. The values had to get into these registers somehow. So the caller may have had to touch memory to get the value of a variable or the value of the address or something. Maybe, maybe not. We don't know. So it isn't necessarily completely eliminated any memory references, right, to pass the parameters. Any questions about that? So we have a different set of conventions that we use to set up the call to the subroutine for the 64-bit machine using the registers to pass the parameters. We have 6 registers that we use to pass those 6 parameters. If you have more than 6 parameters, then you'd have to pass them through the stack, right? So now, instead of pointing to integers, we could point to longs. We can move things around in chunks of 8 now instead of 4. So I could have a pointer to a long and a pointer to a long, and the 64-bit machine is an actual 8-byte long, right? And so you see the move quad word into the RDX register, not move long word into the EDX register. So now we're moving 8-byte longs and swapping their values. But it still just takes 4 instructions, right, to do it. So we can move bigger chunks of data around on our 64-bit machine because our registers are twice as big. So we looked at the history of the Intel processor architectures. We looked at a little C snippets and how it gets turned into some assembly language. And we looked at some basics about assembly language, about how we name the registers and how we talk about the operands, how we move things around. And we looked at both the 32 and the 64-bit. So we'll move on to the next lecture now. Lecture 7. So we want to talk a little more about the addressing modes. Make sure everybody's on board with the addressing modes. We looked at this before, but we'll look at it again. Here's the most complex addressing mode you have on the Intel processor. The three things inside the parentheses, the scaling factor gets multiplied by the index added to the base, right? So it's simulating what you want to do, an array subscript, basically. And we noted that it isn't really doing a multiply, it's really just shifting this RI index to the left. So the S is always a power of 2 because it's really just shifting to simulate that multiplication. The displacement is also always a power of 2. But these things make sense because that's the sizes of our chunks of data, right? 1 byte, 2 bytes, 4 bytes, 8 bytes, right? That's the sizes of these data types that we have that we're going to move things around. So it makes sense, it doesn't constrain us that these things are powers of 2. And then you have all the subcases where you get the combinations. You can leave something out. You don't have to have the scaling factor. It would just take the RI and add it to the base, or add the RI to the base and then add the displacement. Don't need the displacement. Don't have to have that if you don't need it. So you get all those combinations of these addressing modes that you can use to generate an address of something pointing to something in memory. Memory sub, thinking of memory as a big array, right? This is trying to express that what is this subscript into this big array called memory, right? So now we get these examples. If we had F00 in EDX, of course, there'd be 4 zeros to the left. It's 32 bits, right? Not 16. And so that was in ECX, and we had this addressing mode, displacement of 8, and we use the same conventions in writing the assembly language down that we use when we're writing down C. We use the OX to mean this is a hex number. Of course, it'd be the same in this case if it was hex or decimal. So take the EDX register and add 8 to where that points in memory. So the address that you come up with is F008. This one's going to add ECX to EDX. So those two guys get added. That would be the address that we'd go to if we were, say, moving something from memory or moving something to memory. That's what that would mean. This is going to be 4 times ECX plus EDX. So you get 4 times the 100. You get 400 and add that to the F. This is 2 times EDX. EDX contains F000. And you're going to take 2 times EDX, and then you're going to go 80 past there. So 2 times EDX is going to give you 1E000 when you multiply the F by 2, right? And then you're going to add 80 to it, so you get that. Any questions about that? Everybody see why 2 times F is 1E? Think of it in decimal. F is 15. 2 times 15 is 30. What's 30 in hexadecimal? It's 16 plus 14. 16 is the 1. The 14 is the E. Questions? We move on. So now we want to look at this instruction, load effective address, LEA. We've seen this before, actually. So we can use the LEA instruction as a sort of a cheating way to do arithmetic without having to use the more expensive multiply instruction. So if we wanted to multiply something by 12, we could say load effective address long word 2 times the EAX register plus the EAX register is effectively multiplying that by 3, right? And then I could do a shift 2 bits to the left, and I would multiply it by 4. So now I've effectively multiplied what I started off with in the EAX register, multiplied it by 12. So this shows using this addressing mode, load effective address, right, to not really generate an address. We just want to use it as a way of doing some multiplication. So now we want to look at some arithmetic operations on the computer. How do we do some arithmetic operators? What are the assembly language mnemonics for them? Each of these corresponds to an operation that the computer can implement directly. So we come up with these inscrutable, mysterious mnemonics for the assembly language for the arithmetic operations like add, subtract, integer multiply. And then, of course, we have our shifts. Shift arithmetic left long word, shift arithmetic right long word. And so why would we do an arithmetic shift? Well, that would be like if we had an integer, a signed type. We want to propagate that sign bit, right? The shift right is the logical shift. It's not a shift arithmetic, right? And that would have zeros pumped in to the on the left side when you're moving things to the right and vacating those positions. And then we have instructions to do things like exclusive or, and or, just the counterparts of these symbols we were using in C, right? So when we use these operators in C, they just have a direct counterpart with a specific assembly language instruction. I'm going to have to excuse myself for a second. I've got an upset stomach this morning. I'm going to have to go barf, I think. Excuse me. I'll be right back. Mission accomplished. That was lovely. Okay, we'll continue on now. Uh, Good grief. That was the first. All right. So we have these arithmetic instructions, and they're very easy to remember. They just correspond to the ands and multiplies and shifts and that sort of thing, right? So the next concept is we have special instructions for adding one. We don't want to have to always just say, you know, I or add long word one comma some register or something. It's such a common thing to increment and decrement things that we just have a special opcode that means that. It's just increment and decrement, long word. And so then we have the arithmetic negation is negate, neg, and then the bit level thing we've been using to flip all the bits is the not, right? So you could build your arithmetic negation out of this instruction, right? Because you could flip all the bits and then add one and you'd get the effect of the arithmetic negation, which is what the circuitry actually does when you do this instruction here. It effectively does that and then doesn't add one to the result to get the arithmetic negation. So these are all pretty straightforward, right? And there's a whole bunch more. And of course, we have the long word flavor and the quad word flavor of all of these. And then you have the 16-bit flavor by leaving the L off. So we'll move on to the next slide. And what we want to talk about here is the fact that when you write down your C code and you give it to the compiler, a lot of times when you look at what comes out of the compiler, it isn't doing the things in the exact order that you listed them in your C code. And the compiler does a bunch of optimizations, and it may decide that it can compute the same thing you're asking to compute here easier and quicker by doing it not necessarily in the order that you've got it here. So we want to look at this code here and see how it implements this C code. So if we look at, here's our stack. We got 3 parameters, 32-bit calling conventions, right? So the parameters are pushed onto the stack, left to right, going from bottom to the top of the stack there. That's the C calling convention. And so we're going to reach back. We do our little, the call, put the return address on there. Then we save the base pointer and we put the stack pointer into the base pointer. So the base pointer is pointing here now. And we go back 8 locations to get to X. We go back 12 to get to Y. That's because they're 4 bytes big, right? 8, 12, and 16 is where they would live back up the stack and the parameters. So if we look at this instruction here, move long word 8 past where the base pointer is pointing into ECX, what that's doing is it's picking up this parameter X, right? And the move 12 is picking up the parameter Y and putting it in the EDX register. So if we look at the first thing that's going on here in our C code, it's actually adding the 2 parameters together, the X and the Y. But that's not what happens first in our code. We don't add those together till we get all the way down here. The first thing it's doing is this stuff for the green thing, and you'll see why in a minute. This load effective address instruction says take the contents of the EDX register, which is our Y parameter, that int Y, multiply it by 2 and add it to EDX. So that effectively says take the Y and multiply it by 3 and put it in EAX. So now we have the Y parameter multiplied by 3, and now we do a shift arithmetic left long word 4 positions, which is multiplying by 16. So here we multiplied it by 3, here we multiplied it by 16. That effectively is multiplying it by 48, accomplishing the green statement in our C code. So we did that. And now we think of in our code here the fact that it's sitting in some temporary variable. But in reality, that temporary variable doesn't even exist. It's just using this register to hold that value. It's not putting it in memory anywhere in some slot allocated in memory to hold this variable. So you see that other kind of thing going on in the compiled code. So the next thing it does is it's going to do both these two statements in one fell swoop. We want to take X, add 4 to it, and then take that T3 temp and add that to the Y times 48 thing. Well, the Y times 48 is sitting in the EAX register. So if we take the EAX register and we add it to the ECX register has X in it, and then we add 4 to that, we will have done this X plus 4, and we will have done the result of that added to the Y times 48. So that one instruction there accomplishes both of those two statements in our C code. Everybody all right? Now we do this, add long word ECX, EDX, that's X and Y getting added together. And I've got the result of that in the EDX register. And now it's going to say add long word 16 to EBP, right? And put that in EDX. Well, what's in the 16 to EBP gets me the Z, right? 16 back from where the base pointer points gets me the Z variable coming in here, right? So I take Z and put it in EDX and add it rather to EDX, and EDX has this X plus Y, right? So now I've got my X plus Y plus Z. Does that make sense? So then it wants to take this T2 and multiply it times T5, this thing I computed there. So that's sitting in EAX, right? So if I take the EDX and multiply it times EAX, I get that result there. And that's what I want to return, right? And the way you return something from a function is you dump it into the EAX register. Well, by virtue of the way that we set that up and computed it, it was already dumped into the EAX register, right? The thing I wanted to return. So there it is sitting there, and that's the return value from the function. When you get back to the caller, he's going to take EAX as this value you're handing back to him, right? It's always passed in the EAX register, and the 64-bit would be passed in the RAX register. So you see, did all this stuff we wanted, but he didn't do it in the order we listed it because he figured out he could do it more efficiently, leaving these values in these registers, right? If he did it that sequence. So when you're learning your assembly language, the way we learn it is we write little snippets of C code, and then we look at what comes out of the compiler. and see how the computer is being used to implement the stuff we wrote in C, you'll see this kind of stuff a lot of times where it's not a straightforward one-for-one translation of what you've got there. So that's just a caution that that kind of thing will happen, right? So if I had written, instead of all this stuff, if I had just written this expression over here, x plus y plus z times x plus 4 plus 48 times y, that is the same thing that I'm computing in all this junk. It may have, if I just written that one big expression in there and said, return that, it may have generated the same code out of that expression. So here's a logical example. Our C code is using the exclusive OR operator, right? The little circumflex house top. So the first thing I want to do is I want to take the two parameters that come in, which are 8 up the stack and 12 up the stack, right? So this is my Y parameter, the 12 back. It's in the EAX register. And now I'm exclusive ORing the X parameter, grabbing it off the stack with the EAX register. So that's effectively doing this X exclusive OR Y. Once again, notice that the temporary variable that I've declared here doesn't really exist. It's just this register. Now I want to do a shift arithmetic right, long word, 17 positions of EAX, which is taking this T1 thing I just computed and shifting it right 17 positions. So that's that statement right there. And then I got this mask that I'm building, right? I take a 1 and shift it left 13 positions and then subtract 7. Well, the compiler looked at that and said, I know how to do arithmetic. I can just go ahead and figure out what that number is and stuff it in here. I don't have to emit code that computes that up at execution time, in other words. So I just do it once and for all right here at compile time. And then every time you run your program, it just uses that number. It doesn't have to keep recomputing that number. So this is a optimization that's going on in the compiler that we call constant folding. And so then we take the T2, this thing over here that we shifted. It's the thing in the EAX register. And we want to AND it with the mask. And so you see the AND long word just generated that value, ANDing it with what's in the EAX register, which is this result that we computed up here in the T2. So once again, C just mimicking each thing going down the list. The compiler did a little bit of optimization by creating that number, right? So it's the 32-bit calling convention. So you got to pop BP and then you return, right? So the two things here is that instruction, that is this instruction, and then both of those are getting accomplished with this one instruction because it just pre-computed the value. There goes the chainsaw again. Got all kind of craziness happening at the house today. So now we want to look at the condition code bits. You can think of these bits as sort of another register. And in fact, it kind of behaves like that because when we context switch from one process to another on the computer, we have to save off the values of all the registers so that we can restore them back. When we put that process back into execution, it needs to pick up where it left off. The registers need to have in it what they had when we took it away from you. And so the condition codes get saved as well. And so they kind of behave like saving another mythical register. So they have names like CF, CF, SF, 0. We'll see what those mean in a second. The CF is the carry flag. So if I did an operation on the computer and the two things that I was operating on, if I chose to think of them as unsigned numbers, like I did an add, long word or something, and I chose to think of the values that I'm adding as unsigned numbers, if there would have caused a carry out of the leftmost bit position, that would light up this carry flag. There would be a 1 in that condition code. If I did an add and I chose to think of the contents of the two things that I just added as integers, as signed values, not unsigned values, and an overflow would have happened, it would light up this bit. So you see the computer is saying whichever way you want to look at it, whether you want to look at it as unsigned or you want to look at it as signed, he's kind of doing both at the same time, right? Lighting up the carry flag or the overflow flag, saying, which way do you want to interpret what those things were? I don't care. It's all bits to me, right? Anytime you do an operation that resulted in the value 0 sitting in some register, the 0 flag gets lit up. So if I did a move long word from some memory location into some register and the value that I moved in there was 0, that would light up that condition code. A lot of times when we're doing like a loop or something, right? We're subtracting or whatever, we're subtracting from a value till we get down to 0, and then we want to finish the loop. So we want to be able to detect that we just got to 0. And so we'll be doing that by interrogating the 0 flag as to whether we need to branch back to the top of the loop or we need to fall through and get out of the loop. The other one is the sign flag. So anytime you throw something in a register, if the leftmost bit is a 1, this sign flag condition code gets lit, saying, oh, that thing looks like a negative number. The leftmost bit is a 1, right? So we can use that to trigger our conditional branches as well. So these are all set implicitly as a result of executing some instructions, like an add long word or add quad word, whatever instruction you executed sets these bits based on the result of having done that instruction. So the carry flag, right? Unsigned overflow, the overflow flags, signed overflow happened. Signed flag, 0 flag, right? Now, the one caveat, we've been using this little load effective address instruction as a cheating way to multiply something by 3. And it doesn't really do a multiply instruction, so it's cheaper. But the downside is the LEA, load effective address instruction, does not set these bits, whereas the true multiply instruction would set those bits. So if I create an overflow using my cheating LEA instruction, I wouldn't know it unless I did something else to figure it out. It wouldn't bits for me. And we can explicitly set these condition code bits, not just as the side effect of some instruction, but these instructions, the whole purpose of the instruction is to cause the condition code bits to get set. We have different ones of these we will learn. The first one we look at is the compare instruction, right? So if you can say compare long word or compare quad word, whatever size you want to deal with, something here. And you got to watch out because this thing is counterintuitive the way it shakes out. something screwy is going on when they write source 2 here and source 1 there. Why didn't they write 1 there and 2 there? Well, the reason is below. If I do compare long word B, comma A, what that is like is it's saying take the B, the thing on the left, and subtract it from the A. We don't want the result of that value. We don't get the result anywhere like we did real subtract instruction. We just want the effect of, if you did that, what condition code bits would get set. So compare is like subtract the first operand from the second. And so that's why they're writing that backwards there, right? So you have to remember that. It's always tricky. The thing on the left gets subtracted from the thing on the right. Now, if B is equal to A, what's going to happen? Well, subtracting B from A is going to light up the 0 flag for me, right? So if A is equal to B, and I do that compare instruction, I can tell that A is equal to B because the 0 flag will be set after I do the compare instruction. So the whole purpose of the compare instruction is to get the side effect of setting the condition code bits, right? So if when you subtracted B from A, you created a carry out from the most significant bit, right? Then the carry flag would be set. If I did compare BA and I subtracted B from A, right? And the sign flag got set, what is that telling me? That's telling me that subtracting B from A created a negative number. So what must be the case? B must be bigger than A. So if I do compare BA and I look at the sign flag, I know that B is bigger than A, right? So this is how you use this nonsense, right? So the overflow bit would get set by the compare instruction if this is true. A was greater than 0, ANDed bitwise with B less than 0, ANDed with A minus B less than 0, and then or logically or that together with this other big nonsense over there, right? And that's similar to what you were kind of doing in one of your homeworks, I think, at one point. You're saying A came in positive, B came in negative, and the result of the subtraction was negative, right? Or it was the case that A came in positive, A came in negative rather, B came in positive, and the result of the subtraction was positive. So that's the condition that would have set the overflow flag, which is trying to say if you think of these two operands as signed quantities, doing this operation would have created overflow. But notice that the computer's thinking of it both ways at the same time, right? Thinking of it as if it was signed, thinking of it as if it was unsigned, and setting those bits depending upon whichever interpretation you wanted to put on to these values. To him, it's just bits. The interpretation of signed or unsigned is kind of the way you want to think about the data, right? So that's the compare instruction. We have another one called the test instruction. And all it's like is taking the two operands and doing a bit level AND of them together, right? So if I bit level AND two things together and the result is equal to 0, then the 0 flag got set, right? Which means what? That there's no position in A and B where they have a 1-bit set in the same position, right? And so if I AND the two together and then create something that looks negative, has a 1-bit on the left most bit, then the sign flag would be set, right? So we'll see how we use these things to set up for conditional branches and creating our loops and things in a minute. So this is it for today. Unless you have any questions, get your homework in this afternoon. And get it off your back so you can get back to working on your project.
So for 2.85, right? Are we supposed to be turning in the bit representation for a single, what's it called? Single precision, so 32 bits, or are we supposed to just return a equation for the last two? What's it called? Questions.
Which problem is 2.85? Can you jog my memory here?
2.85 is the one where you use the equations. It's the one without the skeleton code.
It's the one that has like 3 parts. First one, they're saying what's 7 look like as a floating point number. Is that the one you're talking about? So the question you're asking is it wants you to show expressions for what those numbers look like, right?
Okay.
It's not telling you what the size of it is, right? It doesn't tell you what the size of the EXP field or the size of the fraction field. It just says it's K and the fraction field is N, right?
Yes, sir.
So you don't have a specific number there, right? So you have to express it as a symbolic expression, right?
Okay. So you have to put
algebra, in that kind of thing. What?
So you have to put in the numbers for the equation instead?
No, you're not putting specific hard numbers in. You just know that it's K bits wide and the other one's N bits wide, right?
Yes.
You don't know what K is. You don't know what N is. But you know that the bias is going to be 2 to the K minus 1 minus 1, right? So you have these expressions that you can use to say, well, what would this thing look like? Does that make sense? It's just you're dealing with it symbolically, like algebra, right? Where you got a variable, you don't know what the value of it is. It's just whatever it is, it's just variable here, right?
Yes, sir. So another thing would be like, do we put in the numbers for like E and F for A in that case? Because it's symbolic. F is just what number is in the fraction field, and E is the number.
I think to get to answer to your question, we should sit down and look at some specific problem and look at it. But that would probably be done in office hours better. Can you make it at 2 today? Can you attend the Zoom session for the office hours? We can work through that in more detail then. So see you at 2 for office hours. Otherwise, have a great weekend.